So you're
No.
They said no. He said no, we are not from selfish. No. Please no.
I will be photographer, taking some photos sometimes.
Oh, sure, yeah.
Working in communications in SPE France.
I see.
Or I have to take the photos.
So yeah, if you could share those photos with me also, that's it.
So
Because then I can send you to the SPE headquarters and be happy to see a good crowd of people.
yeah, I
You're
have
part of the SPE France site. Actually, I was a member for a year, but I never really attended any event. More than yeah.
you can register.
No, I will.
Allah will be happy.
Yeah.
Happy president. He will be happy.
I was not expecting the other big chapter to get it up. Yeah, new event.
Maybe
Wow, very nice number.
Yeah, I'm surprised too.
Very nice.
Everybody can find a chair. There's one extra chair.
Hey, how are you, man?
You guys need some chair? Please.
Yeah,
Take it from here. Then this one is also extra.
yes, yes. Access something for me. Are you access something?
No, I was
Still or something? Never mind. It's a disease that can be cured. How are you?
Yes.
Enjoying the. You're on the spot. Just make. You're gonna.
No, sorry. Everyone's asking about the live.
Yeah, you go. YouTube will link to Go to link.
He said that.
It's gonna be standing room. Maybe here. And there was no one. Yeah. Yeah.
He's maybe sent it before. I don't think.
I have both.
Yeah.
I'm a big fan of its work.
We're missing Rodrigo to do the QHC induction.
I think it's Pierre Blanc that's going
There's somebody from Total Energies
Yeah,
that can.
they left both. Okay. Guys, there are a couple of chairs here.
One, two.
Hello.
Would you prefer to sit or you prefer to stand?
I stand up so they can use my chair.
Well, just if you could stand up, so I'll adjust the microphone.
Is that the right position to be in for your?
Just yeah, perfect. Yeah, that's it. Yeah, I think we'll start in like 1 or 2 minutes.
Ouais, je peux des chaises.
Voilà. On peut commencer si tu veux.
The thing is that they wanted to,
Because
yeah, we're ready.
you will have 8 minutes of your presentation. But
I'm not that long. I make
we
it.
cannot because we're missing, either we just reconnect. So Dr. Murtaza's laptop, because Rodrigo's laptop is locked, because he has his badge.
Yeah, but the thing that the heat. I'll just call.
We can reconnect to his laptop, no worries. Let's pull this line.
I would say, yeah, welcome board.
So if you can, be yours is. Okay. It's coming out.
I can do good, man. I can go good, man.
If we can, that would be great. Do I second completely here?
I just want to.
Talk on this.
Better start.
Yeah.
Either he's looking for.
Let's do the fish selection first. The safety.
Someone forgot this, by the way, at the entrance. In case most of them will leave it here. So thank you guys, everyone. Apologies for a bit of a mix-up we had at the entrance, and in the good sense, we had I call a rich people problem that we had more people than we expected. So it's always good, but that set us a little bit back in the agenda. So just no scheduled drill in case there's any problem or any alarm where we exit calmly to that door over there. You can see the green light, and then to the left, there's Pierre Eduard back there. My colleague, he can also help us, much taller than I am, in case of an emergency, easier to spot. So we're reminded. So we're not on our sense. So thank you for coming and joining us here in Total. Thank you. I won't introduce yet the speaker moderator. I'll leave that to Carla and the rest of the team. But just on behalf of the SP events team, myself here, Constantine, and the rest of the board, thanks so much for joining, and for everyone that has always interest in engaging with SP. Thanks, guys.
Presentations here. The presentation.
Rodrigo.
Yes. Thanks. Focus. Sorry.
Go back to Zoom.
Should I even put it in presentation mode first?
No, Go back to Zoom first.
Now Zoom, share screen, and then we just need to teach.
Because we are online as well, huh? So smile. They are seeing you.
So for those of you who think it's too warm, we apologize. We can't control the temperature from the room. It's a big company.
Okay. Well, as Rodrigo said, welcome everyone. We're very happy to have such a crowded room for the first distinguished lecture of the 2025-2026 season. So my name is Carla Castillo. I'm currently the section chair for SPE France, and with a bit of our team from the board. And we're lucky enough this year to have 3 distinguished lectures instead of 2. So please stay tuned. So a few words about SPE. This is the board. You will recognize some of the people here. So feel free to reach out to us and discuss about our society. Of course, I expect that you are already registered members. Otherwise, you can do it afterwards. So why to join? Why to keep this membership with SPE? First, world's leading technical knowledge resources, a lot of sources to find information, to find studies, to keep up to date in your technical knowledge related, of course, to the energy industry. We go farther than the oil and gas industry. Networking opportunities, a lot of people here with different backgrounds, different countries, so we can, of course, enrich ourselves from each other. Professional development. Myself, I joined the society over 20 years ago as a student. Nowadays, I'm a professional member. And of course, we have the recognitions and awards at all levels. There are the student paper contests, there are awards, regional and international, that recognize the trajectory of the different members. So we are reaching the end of a very eventful year for SPE France. What we do usually monthly conferences, of course, networking events, especially like the one we will have later today, partnerships and collaborations with other entities, with other societies, French and international, European. We have the support to young professionals. Unfortunately, our chair members from your professionals are employed, not here today with us, but they gather around different places at different, at the moment they're organizing 4 every year. So we exchange experiences and lessons learned from the different sections. And of course, the student support. We have a big part of students here. Glad to see you, and especially for the Petrobol competition, but any other plans that you can, you have ideas, we can discuss. So as I said before, 2025 has been started with a big bang with the SPE France 40th anniversary. The event was held last March. We have some pictures here. From it was in the Musée of Arts et Métiers here in Paris, and we have people as special speakers from the industry in France. So the sponsors, you see, all the partners from different companies. And we also held the first Beyond the Borders of this year. We have different countries attending, a big support from SLB, from Total Energies. Again, some of the pictures. This is for the anniversary because both events happen in parallel, but still a lot of people and a lot of exchanges. Last but not least, we had the honor of organizing for the first time in France the Europe Petrobol regional competition. IP School was the champion, and they obtained the 3rd place in the international competition, a big achievement for the student chapter. And still, they managed to welcome over 14 universities that participated, that attended the event. And talking about the last few events for conferences of the year. So some of you maybe attended this. It's already the video is available in our website. You can check it out. Here we of course we have the distinguished lecture today, and please stay tuned in our LinkedIn, in our webpage for the next conferences. Okay, so it's my honor now. Please, Dr. Murtaza Ziauddin will present the lecture for today. So thank you very much.
You need to take over the sharing.
No, thank you very much, Carla. By the time Dr. Murtaza set up, so Dr. Murtaza has more than 3 decades experience in the industry. So we are very honored and fortunate to have him with us today. So take advantage of him being today, ask question, and the lecture is really, I will spoil a little bit. So it's really fantastic. It's new things on carbonate stimulation technology. It's very disruptive technology that will definitely change the game in carbonate stimulation question today, when the technical challenges, the sustainability aspect are challenged. So this type of technologies will answer some of those questions. Without further more, Dr. Murtaza, floor is yours. Go through. Thank you.
Thank you, Tayyip, and thank you for inviting me here. It's a pleasure to be here and also see a good turnout. So thank you very much for taking time from your evening and coming and listening to me. So before I begin, I have to acknowledge that the
Double click.
oh,
So this one?
we double click.
Yeah.
Oh, sorry, not that one. Yes. If I double click it, it moves the slides.
It's in mine, I think, Constantine. In my computer, no? Two more. Click twice again on the just two. That's it.
Okay, let's just keep going.
These already is on the full screen. So before I begin, I would like to acknowledge that the primary funding for this DL lecture program is provided by the SPE Foundation through member donations and contribution from offshore Europe. The Society is grateful to those companies that allow their professionals to serve as lecturers, additional support by AIME. And for this particular lecture, I would like to thank Schlumberger and Total Energies for hosting me. Thank you. Okay, with that, let's, I think we are now it's working. Good, okay, very good. So the topic for today is advances in carbonate stimulation, unveiling the potential of single phase retarded acids, abbreviated as SPRA, so single phase retarded acids.
Yeah.
Now, if I take the reservoirs of the world, right, and basically plot porosity, or maybe I should point over here because plot porosity versus permeability, we get a graph like this, right? So porosity is the reservoir's ability to hold, is the capacity of the reservoir to hold carbonate, hydrocarbons, and permeability is the ability to flow, right? So on this side, where we have the high permeability and high porosity, these are reservoir which produce, because I mean they have a very high permeability and hold a lot of fluids. But as we go towards the left, right, the permeability decreases, and basically stimulation is a way in which we create highways for fluids in these reservoirs to come to the wellbore, right? Here there is no resistance because the permeability is very high, but here there's a lot of resistance because it's very hot. Let me take my jacket off. I'm going to boil by the time you're done. Okay, sorry. So Here the permeability is very high and we don't need a very deep stimulation treatment. But when you go towards these tighter reservoirs, the highways that we create with stimulation need to be deeper and deeper. So starting from these reservoirs at the top here, we have matrix acidizing. So the length scale for matrix acidizing is about 3 meters, about 10 feet, right? So we improve the permeability in about 3 meters to about like 10 feet near the wellbore, because these reservoirs are high perm, and basically the fluids can come all the way from deep into the reservoir. They can come from deep into the reservoir to the wellbore. But as we go to the tighter reservoirs, we need deeper and deeper stimulation techniques. So the next one is fracture acidizing, and this goes to a distance of about tens of meters, right? Then we go into long prop fractures, where we go into maybe hundreds of feet distance. And then we go into the unconventionals, where we have the multi-stage acid fracs. Now, the big thing about SPRAs, the single-phase retarded acids, is that it allows to change these boundaries. Now, starting with matrix acidizing, right? That's the lowest cost technique because we are treating a very small area near the wellbore. As we go deeper and deeper, the cost goes up. Like for fracture acidizing, we are bringing more horsepower, and we are also bringing more fluids that are being injected because you're treating a larger, so the cost goes up. If you go to long prop fracs, we are going much deeper. We are bringing sand and more horsepower. So the cost of the treatment, the stimulation treatment, is increasing as we go along this axis because you're treating more and more of the reservoir. Now, what the SPRA does is it allows us to move these boundaries. So I can apply. So this one is without SPRAs. If you use SPRAs for matrix acidizing, the boundary shifts. So I can apply a lower cost technique to develop my field than with the conventional acid systems, right? So if you have a field development plan based with, say, hydrochloric acid, and you're using matrix acidizing or acid fracturing, you can use SPRAs to help with lower the cost of the field development plan. So this is the big promise from a reservoir perspective. Yeah. Okay, so here's the brief outline from my talk. First, a very brief introduction to carbonate stimulation. Introduction to single-phase retarded acids. Then lab evaluations of SPRA. Then I'll show some case studies and conclude. So first, a very one-slide introduction of carbonate acidizing. So there are two main carbonate acidizing techniques, right? One is matrix acidizing, as they just talked, right? And what we do, again, is we inject acid and we create wormholes from the wellbore going into the formation. And as I said, the wormholes go about 10 feet, 3 meters. We inject acid, it creates these wormholes. And these wormholes are like pipe coming out of the wellbore, right? So they're very high conductivity. Darcy's, multi-Darcy kind of conductivity. So the fluids in this region then can come to these wormholes and produce, right? In fracture acidizing, we inject so fast that the reservoir rock cracks, right? So we crack the rock so we can go much deeper. Okay, and we have these wormholes that's also, so in fracture acidizing, we are etching the face of the fracture. So when we release the pressure and the rocks come back together, there's conductivity left. And that way we can treat several tens of feet of etched fracture length. These are the two main techniques. Again, the difference is based on the injection rate. Now let's talk about the fluids. So we have been doing this for a long time. In 1895, we started with hydrochloric acid, and it's a fantastic acid, right? It gives us the highest dissolution per cost of the fluid. So the dissolution capacity is very high, and we pump from 15 to 28% hydrochloric acid. It's fairly easy to use. The friction pressure is like water, so is much low, very low friction. And environmentally, it is still an acid, but still an acid that goes to calcium chloride brine once it's done. So it is one of the nicer acids. Now, the only thing which is a challenge with this is this very fast reaction rate. So I keep on mentioning that we have a length that we can address with matrix acidizing that was about 10 feet. And this is the main limitation because the reaction rate is so fast that as the acid is going through the wormhole, it reacts. So we can't pump fast enough for it to go any deeper. So that's the limit. So the reaction rate is fast, but everything else is actually very good. So in 1960s, we introduced emulsified acids. Now, emulsified acids, we use 15 to 28% hydrochloric acid, but now we add 30% diesel to it. So it is hydrocarbon external phase, and there's 30% of the fluid is hydrocarbon, diesel or kerosene or something like that. And we have acids which are in a droplets inside the fluid, right? So the 30% of the fluid is unreactive, is diesel, and then the 70% is the acid. So it is excellent at slowing down the reaction because now the acid has to diffuse out of that droplet and come to the rock surface to react. And here's a picture, and it's basically, I mean, if you have the vinaigrette salad dressing, right? It's very much like that, right? So in a vinaigrette salad dressing, you have vinegar, right? And you have olive oil generally. So here we have hydrochloric acid and we have diesel, right? So, but if you look, it's in a microscope, they look very similar, right? And it's very effective at slowing down the reaction rate. But in fixing this, we kind of miss out on these three aspects. So first one is the mixing part. It's one thing to mix a salad dressing for a dinner, but here we are mixing thousands of gallons of acid, maybe tens of thousands sometimes, right? If it's a long well. So to do that on such a large scale, and also to be able to do it in a good way, that means you need to have the droplets of the right size to have the right reaction rate. So the mixing has to be done very well and consistently to have a consistent performance from the fluid. So doing that on a field scale, we are setting up like a small factory if we're doing that. So we lose out on the careful mixing part. Then on the friction pressure, the viscosity of this emulsified acid systems is about 2 orders of magnitude higher than HCl. So, I mean, there's a lot of friction losses, right? I mean, 2 orders of magnitude. So we can't pump very fast with these fluids, especially with coil tubing, right? And since we are introducing diesel, it is environmentally less friendly than HCl. So in 2017, we were challenged to come up with this SPRA system, and this was when they were first commercialized. And we fixed some of these issues, right? So a single phase, so emulsified is 2-phase. We go back to single phase, and that brings a lot of advantages. First, we can go back to the full strength of hydrochloric acid, 28% that we're using. The reaction rate is slow, so I will talk about how we manage to slow down the reaction rate. Mixing is simple because single phase easy to mix. The viscosity is like HCl, so it is much lower viscosity, so we can pump fairly fast. And the environmental profile is similar to what we have in HCl. Okay. Now, let's talk more about what these fluids actually are. And here is a bottle of SPRA. I've taken out the corrosion inhibitor, which gives a little bit of a reddish or yellowish tinge if we add to it, just to show that the water, the SPR itself is very much a clear fluid like HCl. Okay. Now, if you go on OnePetro and search for these class of fluids, this class of acid systems, what I found was that 84% of the time they're called SPRAs. That's why the name is what I'm using over here. But there are other names for it. They're basically the same class of fluids, right? The same class of fluids, but the people call it different names. So one is low viscosity acid system. So all of these are low viscosity, right? So they want to stress. And there's about 7% of the papers you see in mentioning by LVAS. Then there's single aqueous phase retarded acid called SPRA. I think this actually means the same thing as this, but it's about 5% of the people are using that. And polymer-free single-phase delayed acid, PFDA, and only 4% of the people are using that. But all of them are polymer-free, right? So they just want to stress different aspects of it. So it's all of them are low viscosity, all of them are delayed, all of them are single-phase, etc. Right? So the same class of fluids. Now, what are the main components of this fluid? Is hydrochloric acid. We can say 15 to 28% hydrochloric acid, and then we add 1 or 2 different retardants. And I'm going to talk about what we add. Okay. And but an important thing here to mention is that compared these systems to the organic acids and chelants that we were using earlier before these systems, the main dissolving power for SPRA comes from hydrochloric acid. Okay? For an organic system, if like you're using formic acid, acetic acid, or citric acid, the dissolving power comes from that organic acid. Now, hydrochloric acid has a much higher dissolving power than acetic or formic, 3, 4, 5 times higher. And the cost is much lower. So in going from SPRAs, so in going from these organic to SPRAs, we gained a lot in dissolving power and a lot lower cost compared to organic acid systems, right? So that's a big advantage. So these are also single phase. The chelant systems and organic acids are still single phase, but SPRAs is a different class because the dissolving power still comes from hydrochloric acid. We just slow down the reaction rate of hydrochloric acid. Yeah. Now, let's talk about the mechanism of how, what the main challenge is and how do we slow down the reaction. So what I've tried to show over here is my wellbore, where I introduce the acid, right? So this is acid coming out at full strength. If I'm injecting 28% hydrochloric acid, it's coming out of the wellbore at 28%, right? And I've tried to draw a wormhole, and typically a wormhole is about 3 millimeters in diameter, so base thin, right? 3 millimeters. And the typical length that we get in the field is about 10 feet, or that's about 3 meters. So it's 1,000 times longer, right? We're going to 3 meters, 1,000 times longer than it is wide, right? Now, the way I think about this, and I'll show you some pictures here, is like a very thin channel, right? So my little proton, my HCl is sitting in a little river which is flowing very fast. And as soon as it hits the wall, it dies, right? Because the reaction rate of hydrochloric acid is so fast, there's only mass transfer limited. So when we say mass transfer limited, what we mean, it is the mass transfer of the H plus from the bulk to the wall. That's the limiting rate, right? So as soon as it comes to the wall, instantly it goes into water. It dies, right? So our goal, and the main challenge, is how to make this proton survive to the end of this, right? And I think it should be pretty clear that I have to deliver my protons to the tip of the wormhole for the wormhole to advance further, right? If I don't have a live protons, live acid to the tip, my wormhole is not, I'm just water at that, right? I'm not going to advance further. If I don't deliver at the right rate, I won't advance further. Right? So that's the main challenge. How do I protect my proton where I have a very thin channel, 1,000 times longer than it is wide, and it cannot touch the walls? Right? That's the chemistry challenge that we have faced with. Now, our solution that I showed earlier was emulsified acid. And what we do is we put the little proton on a little raft, right? So it has protection surrounding it. So if it hits the wall, it doesn't die, right? And that is very effective, right? Because then the proton can go through the river and come out alive at the tip, right? So we fixed that. But what was wrong, what we lose is that the amount of rafts that we add is 30% of the fluid. So that fluid is unreactive. And if you have a whole bunch of these rafts, the viscosity is very high and we can't pump fast enough. So we gain one thing, but we lose two things. So when we were working with this SPRA, when we're trying to see how do I do a big change in this, right? A step change in this, is we had to completely rethink the problem. And we fixed two things to reduce the reaction rate. First is the diffusion coefficient. Now, you may be wondering why I have a picture of a dog next to, so this is supposed to be a very happy, energetic dog, right? And what it does is basically, it keeps on running around. And why I have a picture of this is because my proton is like that. My proton is very small, right? It's only 1 molecular weight. And the diffusion coefficient, which is like running around, is 10 times higher than diffusion coefficient of normal ions. Like if I compare with sodium, chlorine, potassium, calcium, those are much heavier, right? My proton is only 1 molecular weight. So it has a diffusion coefficient is 10 times higher. So just imagine it's like buzzing around like this, and it has a lot of chances it will hit the wall. So if I reduce my diffusion coefficient, with mass transfer limited, I reduce diffusion coefficient, I reduce my mass transfer, and hence I make my proton last longer. So how do I control this dog? Is basically I put it on a leash, right? So I tie to something much heavier than he is, right? So then it can walk along this path, and imagine this path is my wormhole is going through, and I am controlling the dog so it doesn't go into the sides, right? That's one way of doing it. And in chemical terms, what we do is I have my little proton here. This is my proton. And I tie to a big molecule. This is, by the way, methane sulfonic acid, right? There are many other acids that we use, but this big structure is methane sulfonic acid. So molecular 1, and the rest of the molecule is 95 weight. So I have a 1 to 100 times ratio almost. So I'm sometimes I pour a proton with something times 100 times its weight, so it's very securely tied. Actually, it's kind of locked, and it is very effective at reducing diffusion coefficient. Now, this ratio is 1 to 100. So if you thought that person in that picture was big, that's a ratio of 1 to 20 almost, right? I mean, if you compare the weight of the dog versus the person, this is a 1 to 100 ratio, right? So just imagine a person 5 times bigger than what I had shown in that picture, right? So it's one way of doing that. The second chemistry trick that we play is by controlling the surface reaction rate. And what we do is, so as I said earlier, as soon as my proton hits the surface, it dies, right? It's water. So what we do here is we coat the surface with a surfactant, right? So now it can hit the wall and bounce right back off. So it doesn't die when it hits the wall. So we coat the surface of the wormhole or the fracture face with a surfactant. So these two techniques are very effective, right? Can anybody guess which one is more effective? Is one number one or number two? Maybe I can do a show of hands. Number one is more effective?
Number two.
Okay, so most people are saying number two. Okay. So if you look at its ability to control reaction rate, number two, by the amount of substance we put into it, number two does 80 to 90% of the work. Right? Now, I'll talk about number one also, but in number one, what it does, it binds the proton. Right? And when it binds the proton, it slows down reaction rates for everything. So you must have seen advertisements and I think safe acid systems, right? I mean, so that's what they're doing is using a big molecule. I'm not saying they're using methensulfonic acid, but there are other molecules which are heavy, which kind of bind the proton. So the reaction rate is reduced for all different kind of. So if you are putting your skin, you're putting your hand in the acid, it will also protect, right? Because so this has a different. It's slowing down the reaction for everything, but to slow down, to capture one proton in molecular weight, I have to add a lot bigger mass to it, right? So this is expensive to do, right? But it does make the acid safe because it controls the proton for everything. Now the surface reaction, this is a surfactant, right? It's very specific to what surfaces it sticks to. So the way these surfactants are chosen are that they stick to carbonate surfaces and they protect, but they are not slowing down the reaction rate for everything, right? So that's the main difference. So some companies have only mechanism 2, they reduce the surface reaction rate and they have a much lower cost fluid because this is the more expensive part. Some companies only focus on this and the cost of their product is much higher because for each little proton, I have to add a lot of other things to slow down the reaction. And some companies use both of them. Okay? And it's kind of interesting story is because when we were first asked to kind of work on this fluid, we only focused on this one. And the first generation of fluid that came out was only focused on the diffusion coefficient. Because if you look at the literature, everybody talks about mass transfer limited, and there's a lot of publications, a lot of chemical compounds that slow down the reaction rate. So we knew this and we spent several years doing that. And it was just by accident that we discovered the second mechanism. And we were surprised. So I think a lot of science advances by good accidents or just learning from. But fortunately, now we tested that, and this does most of the hard work in slowing down the reaction rate. All right. Okay, now I would like to share a case study with you. And this one is I've taken this from SPE 20623, and I've modified it a little bit, right? The pay zone is about 82 feet. The temperature is pretty hot, but still, I think even hotter than the room here. 356, 356 degrees Fahrenheit, right? The initial oil production was 300 barrels per day. The skin was fairly high, 200, right? And I did a first stimulation treatment. We did a first with 28% hydrochloric acid, and there was no increase in production after that. As we pumped acid, nothing. Then we did a second stimulation treatment, again with hydrochloric acid. We didn't change the fluid. And this one resulted in 3,000 barrels of oil per day, right? So we started with from 300 and went to 3,000. Now my question to you, and we can do like a raise of hands again. Sorry, let's do this one. I mean, number one, is this treatment a success or is it a failure? So people who think a success can maybe go up. So nobody, I guess, right? But I was presenting this as a university and they said this was still a successful, and their argument was that yes, they did not gain in production, but they learned a lot of things. Yeah. So this is a matter of perspective. But more interestingly, the second part, right? Is it a success or is it a failure? So, okay, so success, maybe hands up, I guess, or hands, raise your hands.
It depends.
So some people are still very undecided. There's no wrong answer for this one. There's no wrong answer, right? Okay, so
I would also comment that the first treatment, it happens in a rock which isn't uniform. So it could have created some pathways that were then used by the second treatment to connect better to the formation. So if it was the same well, and it's hard to say that it was.
it's the same well, but yeah, it didn't go into any zone. That was the reason it did not increase. But there's a good perspective. I didn't think about that.
Yeah.
But so this is a tricky question because it depends on your perspective, right? So in this is an economic success. The second treatment is an economic success because the production went 10 times and the treatment paid for itself in no time. But technically, it is a failure. And let me show you why. So if you use this hydrochloric acid, your wormholes don't go any far. They very near the wellbore, right? So the skin after this, the second treatment was skin of 0, right? In carbonate acidizing, we get a skin of -3, -4. So if they had chosen, I mean, most people, I think, if you talk to them, they're using hydrochloric acid at a very high temperature. They should not be using that, right? And if they had chosen the acid more carefully, right, like an SPRA, they would have gotten to about 6,000 barrels of oil per day, right? So yes, technically, economically, the treatment was successful, but from a technical perspective, they only got half the production they were supposed to get. So it's a technical failure, but economic success, right? The company, in this case, they considered an economic success, and they did not go back to the well, right? They were happy with the 3,000 barrels. Now, this is only one well. Now, let me look at a larger case study where I have 600 wells, and each little dot over here is a well, right? With the pressure buildup and everything. So the red line is the Middle Eastern reservoirs, right? And the green one is the North Sea chalk, and they pretty much have the same pattern. The few things to notice over here is that 80% of my stimulated wells have a skin of -3 or lower. So in previous example, there was a skin of 0. So we were quite confident we should get a skin of negative something, right? So 80% of the wells have a skin of -3 or lower, but around 50% is about skin of 3 point something, right? So I have a little table over here which shows the skin versus the length of the wormhole versus the productivity index, right? So if you start out with a well with some decent skin, say 30, right? It's 0.2 over here, and you jump to something like -4, there's a 10-fold increase in production. So getting more production or a big increase in production from most carbonate stimulation is routine. Now the question is that these treatments are only with hydrochloric acid. Very simple design. 75 gallons per foot. Just pump the acid, 600 wells, and the question is, what does SPRA bring to this? Right? I mean, it seems to be doing very well, right? Why do we need to have something different? So we don't have that many wells, but I mean, if you do the data that we have, the graph of SPRAs would be something like this. It would be lower skin than your HCl. But the question is that we start out in an SPRA, we start out with hydrochloric acid, and I'm adding stuff to it, right? Sometimes 1 retarder, sometimes 2 retarders. So my cost of my fluid has to go up, right? It cannot be the same as 28% hydrochloric acid because I take 20% hydrochloric acid and add expensive chemistry to it, right? So the question we are trying to answer is, what is the value that we create by adding that chemistry? So is it the increase in production offset the increase in cost that we have because of that data chemistry. And for that, for each reservoir, I mean, that question has to be answered by doing lab tests and evaluating to see, is the reservoir characteristics really justify use of a more expensive fluid, be able to increase production or not. And for that, we have a lot of lab tests, and I will focus on those. So there are two main kinds of testing that we use. So one basically is a core flow test. We take the reservoir core, inject acid, right? The second one is the reaction rate measurements. I'm going to focus mostly on the core flow test because these reaction rate measurements were popular in the first version of this, where we had only one mechanism, the diffusion rate mechanism. And in those systems, they were measuring the diffusion rate and they were trying to characterize the fluid. But now I don't see too many of these, so I'm going to focus on the core flow test only. Okay. A core flow test is actually fairly simple. We take a core, I mean, an outcrop core or a reservoir core. The typical size is about 6 inches by 1.5 inch in diameter. We inject acid and we monitor the pressure drop across the core. Right? So as we inject acid, it creates a wormhole. And this is the CT scan showing the wormhole. Right? And as the wormhole progresses, right, the pressure across the core starts to go down. And when it gone through the whole core, the pressure drop, because it's like having a pipe through the core, right? So the pressure drop is almost zero, and we call that point pore volume of acid to break through. Right? So we take different acids and we can start plotting it. But the idea is that we keep the length of the wormhole constant, which is the length of the core, and we keep on changing the volume, and the volume is the parameter that I try to find out from here. Now, if I inject the acid at different rates and I calculate the pore volume, right, we get something like this in which we get different shapes. And only at the optimum injection rate, we get the nice wormhole. If I'm lower than the optimum rate, I get phase dissolution. That means I dissolve the whole core and it doesn't go very deep. Right? So my volume of acid that I have to pump is much higher over here. Right? Then I hit the optimum injection rate and then go above the optimum. Right? Okay. Now I can do this with different acid systems. And this is the plot of HCl. And this is the log scale. And this is also a log scale, right? And this is SPRA and emulsified acid. There are two things to notice over here. First, the SPRAs are all lower than HCl, right, with emulsified acid. And the curve is flat, which means we are less prone to the fluctuations in the injection rate, right? And this is very important when we start injecting with the coil tubing. Coil tubing are limited by the rate, right? So we are here. So if I'm limited by the rate and something of the big wells, I cannot inject fast enough through a coil tubing, right? So SPRAs will give still a good performance, but you're using hydrochloric acid, you may be pumping a lot of acid. Okay. Now, so there are two sets of papers, and there's another one in this series, but I would like to point out these two papers from ADNOC, which is Abu Dhabi National Oil Company, and they did a favor to the industry because they took all the SPRAs that are commercially available, and they could find 8 or 9 of them. Right? The different service companies and different operating companies have their own SPRAs. And they took all of them and took very standard Indiana limestone cores and acidized all those cores. And they did literally hundreds of these experiments. So it's a very good paper to view if you're looking at just a general view of SPRAs. So they kept the temperature because this is temperature of the interest, 250 degrees Fahrenheit. There's a fairly tight 1 to 5 millidarcy, right? And in the 9 commercial SPRA systems, they found that 4 of them were actually top of the class. Okay? And then this did the same thing with dolomite, similar temperature, and also found that 4 of the 8 were actually 50% of them were really good, right? Others were not so good, and in some flow rates, they were actually worse than hydrochloric acid, which means you're spending a lot of money for the SPRA, but actually you're getting worse performance. So it's very important to be careful in choosing the SPRA for your application, right? And all this is published. But for the systems that work, right? So 4 of these, 4 out of the 9 that worked, what you see is this green curve is the SPRA curve, and this curve, this yellow is the hydrochloric acid curve, right? So if you're in the low injection rate, the SPRAs can be 10 times more effective, right? An order of magnitude more effective than your HCl. So you're injecting 1/10 of the fluid, and that's a big thing, right? If you're in the middle part near the optimum, they are about 5 times. It's still a pretty big number, 5 times. And if you're in the very high flow rate range, you're about 2 times more effective. So 2, 5, all of them are actually showing a lot of value that the SPRAs create. And operationally, field-wise, we are mostly in this region, in the 10 to 5. So the number is between 5 to 10 times more effective for this temperature system, which is a pretty big number. And this is not any service company. This is an operating company testing a wide range of SPRAs available. Now, the second type of testing we do is we keep the volume constant. So in the previous test, we kept the length of the core was constant, and the wormhole is basically the end of, right? Here, I keep the volume constant, and I inject the same volume of acid in each. So I take acid 1, inject the same volume, and measure my wormhole length. Inject acid 2, same volume, same injection, measure my length of my wormhole. And what we see here, so this is basically 2 systems. I have hydrochloric acid 28% and SPRA 28%. Right? Injections rate same, 1 cc per minute. Right? The volume is the same, 0.41, half the pore volume. Right? And what we did, so I can't see the wormhole length over here. So what we did was we did a CT scan of that. And after the CT scan, we printed the shape of the wormhole, and actually I've brought this with me here. These are the things. So this one is here, this SPRA, and this is SCR, right? So this is like a 6-inch core, 1.5-inch diameter, right? But now you can see through it. So I'll pass this around. You can see for yourself what the wormhole looks like. These are actual wormholes that we just CT scanned and printed it. So since the dissolving power is the same, right? Because same acid strength, same volume, same dissolving power. The question is where the dissolution occurs. So in HCl, as I said, the reaction rate is so fast that it dissolves a lot in the entrance of the core. You can see that big hole in the beginning, right? But it doesn't go deep. SPRA, same dissolving power, but now the resolution is more stretched out into a thin wormhole, right? And that's what you need for your resolution. Okay. All right. So going back to the case history that I mentioned and said, okay, we'll get a lot longer wormhole with SPRAs, is just because of this fact, right? And the temperature, this is also fairly hot, is about 225 degrees Fahrenheit, right? And if they had chosen a different acid system, right, they would have, got a much more negative skin, at least some negative skin, right? They were at 0, they've gotten a -2, -3 kind of skin. Right? Okay. So now let's look at some case studies, and we have a lot of case studies around the world. I'll just highlight a few of them. How are we doing on time? Okay?
Yeah, okay.
Yeah, okay, so yeah, we're just approaching the end of things. Okay, so I'll just quickly highlight some of the case studies that we were used. So first one is North Kuwait. This is an acid frac in a tight carbonate. And the SPE paper numbers are here if you want to look them up. So they compared their production to emulsified acid and the production from SPRA to emulsified acid. They saw a doubling of production, right? Because they could pump much faster with SPRAs. And that led to a change in completion strategy for that operator. That, if you remember the first slide I showed you, where we show that we could completely change the field development plan and the completion strategy, right? So they changed the completion strategy for this. The second is also from Kuwait, and there is matrix acidizing through coil tubing. And here they can pump much faster, and also the SPRAs are much more compatible with the diverters that we use in the field. So that's like a perfect combination for those. And they got very good results here. Then the second one is from Saudi Arabia. It's a multi-stage acid frac. They saw a 40% PI increase over emulsified acid. That's a pretty big increase. I think they have this, and then they have about 40, 50 of these in Saudi Arabia that we used. In Kazakhstan, there were 2 acid fracs and 3 matrix that they compared in this paper. They saw 30% more efficient for acid fracs. By efficiency, mean volume-wise, right? So you use less volume for the same kind of skins. 30% more efficient for acid fracs, 44% or half the volume for matrix acidizing. Now, this one is a particular nice one, and I'll talk more about this in detail. This one is from UAE, ADNOC, right? And this is a fairly long well, 25,000 feet, right? And I have that on the next slide. And basically, they have this 2 wells. One is the SPRA well. The other one is hydrochloric acid. And they're very close to each other, right? So the open hole length, 25,000 feet in both cases. 8.5 inches is basically the open hole size. It's into compartments. This one has 32, this one has 35. The perms are similar, reservoir pressure similar, and the initial skin is similar. And on the saturation map, if you look at them, they're very close to each other. But these are like really the most, as close of wells they can get in this kind of in carbonates, right? So it's similar saturation and all basically very, very similar parameters. Now, the result that we got from stimulation is post-stimulation initial production versus SPRA, right? 15% increase compared to hydrochloric acid, right? Now, the more important, the long-term production, which is 6-month production, we saw a 37% increase in production, right? So both of these numbers are quite impressive for a pretty big well, right? So 37% increase and 15%. These are the obvious things from the graph. But one not so obvious thing is look at their target. So their target compared to HCl is still, if you look at them, they are, even with the hydrochloric acid treatment, they're exceeding the target, right? So if you go up to say, okay, well, I mean, is your treatment, carbonate stimulation treatment, a success? Yeah, we are doing great. All our jobs are going, exceeding the target, right? But the target this is the same situation, but slightly in a different flavor, what I showed earlier, where we thought that 3,000 barrels of oil per day was a success, right? Because if you don't know any better, right, you don't see any reason to say this is not only a challenge with SPRAs when we introduce new SPRA, but any new technology that we introduce, because there's really no real good benchmark. The benchmark is based on the old technology, and you have to take some leap of faith here, right? So, but luckily for this well, there's another very big advantage besides production with SPRAs, and this was very important for this well, is because this well is so long, right, and it's offshore. So the number of boat trips they had to make to treat this well was enormous. It's almost a logistic nightmare to keep on going, filling the acid tanks, coming back, going back, coming back. It's 25,000 feet of length, right? So having a system which reduces the volume by even half, right, even 1/5 or whatever number that they found in their own study is a big deal. So production is big, right? But if you're saying, oh, we're exceeding the target, we don't really need any help with the production, but the logistically part is also a big challenge offshore. And that also SPR is a big advantage that is not often highlighted, right? That we can reduce the volumes and have a much more logistically practical system, right? All right. So I had the pleasure of hosting a forum on SPRAs, and this was in the formation damage meeting in Louisiana on Lafayette, right? I know some people may attend from here, but it happens every 2 years, and I invited carbonate stimulation SMEs from Shell, ExxonMobil, ADNOC, and Aramco, right? So if you look at the carbonate assets worldwide, these four companies really control most of the assets, right? Between Aramco, ADNOC, Exxon, and Shell. And the main conclusions from that meeting, from that forum, were basically these three that I have. So first, more with less. So I think we have enough data to say very confidently that the volume of SPRs that's required for the same level of stimulation is much less than hydrochloric acid, right? So we get better stimulation with the same volume. This one was highlighted by ADNOC, which was the long well, that in long wells where we're pumping a lot of acid, the only practical, so even if it's onshore, right? I mean, offshore is even more big benefit. But for long horizontal wells, right? Just because the horsepower, the equipment mobilization, the days to do, and some are basically just constrained by the availability of the boat, right? You can do 5 wells instead of just 1 well if you're reducing the volume by 1/5, right? So this one is actually a really big deal in many cases. And the environmental impact, if you reduce the fluid volume, you reduce the boat trips, everything, the environmental impact is better than other acid systems. Now, this is just my conclusion slide. So SPRAs, I mean, I hope you agree that they provide much better stimulation option than hydrochloric acid. And what we would like to do is to even extend this even further. Like, I mean, right now, we can double the length of a wormhole. We can double the length of the acid frac with SPRAs because I'm slowing down the reaction rate. And the question is, can I go even further than that? Now, I have a very important non-technical slide, which I will show. This is required by SPE headquarters. They want to hear from you. And I have, I think, a very large audience. If you could take a few moments and just flood SPE HQ with their feedback.
Yeah, thank you very much, Dr. Murtaza. Well, thank you. It was a really insightful presentation, so we thank you for that. I think we all learned how we can do more with less. Definitely that's the takeaway I'm having from this. And thank you very much for this. We'll take some questions from the room and some questions online. I'm having my phone, not because I'm having my phone, but because we are online, right? Yeah, please.
Loved your presentation, so thanks for coming.
Thank you so much.
And then educating us. Practical question, can you re-acidize and still see tangible benefits? So imagine you've acidized 5 years ago, you chose a different fluid, go back, do single phase acid.
So it's a very good question.
Sorry, Dr. Would you mind repeating? Because
People can't hear. Okay, so the question is that can I re-acidize a well after 4 or 5 years, right? So that
Just
okay, so when you re-acidize the well, I mean, so when the well is producing and you get formation damage like scale, or so these carbonate stimulation, I mean, acids are good in a way because they can bypass the damage, right? So initially, when you produce the well, you may not have any scale or formation damage that the first treatment removed maybe the drilling induced damage, right? But then during the life of the well, you may get scales or asphaltene deposits or things like that, and you can re-acidize the well to bypass that damage. Now, there are two aspects that I would like to stress. One is each time, so in matrix acidizing, the wormholes are very stable, right? So they last years. But in acid fracs, in some acid fracs, especially in softer rocks like chops, Ecofist Reservoir in the North Sea, Walhall, right? All of these are very soft. So in those, we have to re-acidize because the fracture heals itself. I mean, the heal is basically the rock is so soft that over time under stress, the fracture disappears pretty much. It heals itself, right? So we re-acidize to be able to create a new fracture. Right? Now, in a matrix acidizing, if you have a good skin, right, if the skin is already -3, -4, then the question is, what is the best value? Do I pick a brand new well? Suppose I have a fixed budget of my stimulation budget, right? So is it more valuable for me to acidize a new well or spend that money on acidizing a well which already has a negative skin, -3 or -4, and how much improvement can I get on that? And that is a candidate selection and optimization. But yes, I mean, definitely we can technology is not a limit, it's more of an economical constraint. Okay, for acid fracturing, we have to, and some of these acid fracs only last for 6 months or 1 year. And there's a lot of technology in how to improve that, but we can re-acidize those. Very good question, sir.
More questions in the room?
Oh, sorry, go on, yeah.
Yeah, well, it relates to Pierre question. Actually, I work for fields where carbonate fields where the acid jobs happen in irregular intervals because of the deposition of the increase of skin because of the deposition of carbonate or calcium in the fractures. Is there, in the same way that you it's been compared that the SPRA versus the acids, you need less acid, there is a comparison regarding the duration of the effect to of the SPRA versus acid.
So when you said, are the fields that you're mentioning sandstone fields or they're carbonate?
No, carbonate.
They're carbonates and they have to re-acidize.
Yeah, because calcite depositions due to high water.
So there's a scale. So I call them scale. So that you have calcium carbonate scale that comes with water production.
Yeah.
And you will fill up those channels that you created because wherever there's a pressure drop, calcium carbonate would deposit. And yes, you can re-acidize to reopen those channels because you're redissolving the porous medium and creating wormholes again. So the wormholes that were plugged with calcium carbonate deposit can be reopened because then you have different pathways with acid.
Sure, but the duration of the effect.
Oh, so no. So I guess it has a secondary impact because the deposition occurs in the first place because of pressure drop. So if you have a good stimulation treatment, in the first place, you have a less pressure drop to begin with that prevents your scale formation. Actually, I have a couple of more slides on that. Which is a very deep question, right? Because you don't see it in the first 1 or 2 years of production. It's only after you see the scale that you realize that you didn't do your acid job properly. Right? If you have done your acid job in which you cover the entire interval, right, and not just one zone, so your pressure drop is spread over much. Then you have water breakthrough coming much later now because you're not producing only from one layer. So it is a whole series of events happen, but many people forget about it, right? Because the initial skin will be very similar from these wells, and only after years, maybe, or in most cases years, 3, 4, 5 years, you realize that since the initial acid treatment was not good, you are seeing all of these problems that are coming forward. And yes, SPRs can help with that. Very good question.
More question?
Yeah.
Masi?
So how is the SPRA performance compared to other traditional emulsified acids in terms of, like corrosion control and the penetration depth?
So, good. So for the reaction rate part of it, they are similar to emulsified acids. Right? Now, and that's reaction to carbonate surfaces, right? When you talk about a reaction with steels and tubulars, there's the corrosion part. And we have good corrosion inhibitors that control all the way to 350-ish kind of temperature range. So the corrosion inhibitors are different than what we use for emulsified acid, but they're good corrosion inhibitors today. And we would not dream of doing an acid job without a good corrosion inhibitor package. And the first thing we do is test. We get coupons of materials of the pipe, right? Pieces of pipe material, and we have corrosion inhibition tests for 24 hours, 48 hours to see if the corrosion inhibition package is good enough. And it's very similar to what we use for hydrochloric acid. So the corrosion rates are similar, and the corrosion inhibitors that we have today are actually very effective in controlling it quite well. But higher the temperature, the bigger the challenge. Yes,
Go ahead, Dejan.
Good evening. Thanks for
Okay.
the presentation. Sorry.
It's okay.
Yeah, sorry.
Yeah.
Thanks for the presentation.
Thank
It's
you.
really interesting. My question is about the comparison of SPRAs on limestones and dolomites. Are there any comparison in mixed rocks? Because sometimes you have like 20-30% plastic material in your rock, and how does it affect? Because when we did a project with an SPRA, and actually we saw that it was actually ramifying in the cores with some plastics. So.
No, it's a very good question. May I ask what region of the world was that? Because in most
West Africa.
West
Because,
Africa, yeah.
All the examples in the Middle East, I guess you get
Yes,
pure carbonates.
yes,
to
because
deal with,
exactly. There's a reason I asked, because in Middle East, if you look at most of the line, they are 95% plus calcites, right? Mostly limestone or dolomite. But only in West Africa and also in Egypt, also in pre-salt in Brazil, you get a lot of aluminosilicate minerals, the silicates coming with that. And in some cases, we have done some trials and SPRs are more effective. In other cases, I think the traditional acid systems, we had a lot of success with VES fluids in these reservoirs, because the VES fluids have surfactants in it, which somehow stabilize the fines that are generated as we create the wormholes. And I think those could be more effective in that. But since there is such a wide variety of those kind of reservoirs, right, that I can't give you that this works all the time, right? It has to be, I think we're doing the right thing by taking the course and running the test, because it's very case by case basis. It just depends on what path the wormhole takes through that porous medium. That does it dissolve more fines or does it can progress? And yes, if it hits the clays and all of that, it's going to create a very ramified wormhole. And I've seen both of those, and it's a very reservoir specific question. But nothing against SPR, it still would do the same thing. But in these systems, I had a lot of luck with VES fluid systems.
We do one last question. I read it from online, so it's
Yeah.
take more time.
Yeah, and then we will have Dr. Murtaza with us on the afterwork, so we can have more questions. But I will take one from online. I think some of them were answered, but I will take this one that I find particularly interesting from John Williams. We always quote production gain immediately after the treatment, but are gains always long term?
So that's a pretty wide question, right? But I showed an example in which we were able to, the ADNOC example, where we were much higher in long-term production. And the long-term production was only 6 months after, which was about 37% higher than the comparable HCl well. And the main reason was that we were able to do a much better stimulation treatment, so the stimulation was much longer lasting than HCl. But I mean, is it we see in many cases that if the stimulation treatment is designed properly, meaning they're well distributed, they have a longer life, and that is like a secondary benefit of SPRAs.
And the more contact with the reservoir,
The more stable, the less
less
drawdown.
frequency of operation
Exactly.
later.
So that's like a side benefit of doing a SPRA.
We have a lot of questions online. We'll not be able to take them, but we'll make sure to answer them after offline, and then we can send some.
Sure, I can,
answers to them. We will collect the answers offline for the people who are online,
Yep.
and we will answer you one by one. With that,
Just key messages, quick ones, just, you guys might have realized that when you read the QR code, you might have not found SPE France.
Rodrigo, would you mind going closer to the mic, because the same questions came from people online.
So you might have noticed that when you scan the QR code, SPE France, if you pick.
Yes.
This one.
Well, there's no SPE France on it?
Yeah, guys, so for those that have kindly tried to give their feedback through the QR code, you might have seen that the SPE France is not amongst the options, because this is actually a third deal we're getting thanks to you guys and Doctor. So, but we invite you to visit spe.org/DL to give feedback. And of course, you can also send feedback to us by email to contact@spefrance.org, and we will relay it and forward it back to the DL organization. And just the second one is, once we conclude, I will escort you to the.
he has it now.
There's SPE France. Name.
No, is there? Oh, okay, great news. And just as final note, when we leave, we'll escort you down to the exit. But please, afterwards, do join us for the after work that we prepared for you guys.
Yeah,
Yeah.
if I didn't get to answer your questions, you can always search me on LinkedIn or in my SLB email, and I'll try to get to them.
Couple closing remark. Again, I want to reiterate our thanks that you
No,
made it to Paris and you joined us for this. So thank you very much, and I would like to the audience to upload it. And the second one, thank you very much for Total Energies for hosting us again. So that's great to allow these gatherings, and for all of you who are here. So now we follow you, Rodi. Huh? We follow you.
Okay, guys, so we'll take it to the end. Yeah, what? I'll take myself. I'll take you back. Be sure not to forget any
Here or